computing and edge, and in particular, so to the wireless world. James.
Yeah, thanks a lot. Okay. So good afternoon, everyone. Thanks, Martin, for this introduction. Thanks for inviting me here for the summer school. My understanding is we have now and we have tomorrow morning, right? We have like an hour roughly now. We have also roughly an hour tomorrow, right? And my understanding is
it's up to you.
It's up to me. That's good.
I mean, what some of the others did was sort of probe where interests are and where there are particular points, and maybe that could be a follow-up.
Yeah. Okay, good. So what I basically thought is that we now turn a little bit to edge computing or fog computing and so on and so forth. But at the core of this, the way I see it, there's like a new form of internet arising. And that's what I'm mainly going to talk about today. And this is what we're talking about today, mainly about high layer concepts, visions, challenges. And then tomorrow we're going to devote more time on a specific, let's say, use case. And we're going to go a little bit more into science. And my understanding is there was a paper sent out, right?
Yes.
So by tomorrow morning, 9 o'clock, right? Yeah. You're all experts in that. Okay, let's see. Good. So quick first introduction of myself. My name is James Gross. I'm now for 6.5 years here at KTH. I'm an associate professor. I'm mainly working in wireless networks, so I'm a networking guy. I got my PhD actually from TU Berlin. I stayed in between Berlin and Stockholm for a couple of years in Aachen at RWTH University there. So that's kind of like my academic side of life. I'm also a co-founder of a company that is commercializing intellectual property in wireless networks for industrial automation. This company is called R3 Communications. It operates out of Berlin. It's a different story. We're not going to talk much about that or at all about that today or tomorrow. Now, research-wise, I started working in cellular networks, and that was by the beginning of the 2000s. There was lots of hype. The internet was kind of like, from a business perspective, it was in this exponentially scaling time frame. People were pouring lots of money into spectrum. Perhaps some people remember that. There were spectrum auctions by the end of the 90s, by the beginning of 2000s, all around Europe. And cellular network operators poured lots of money into these spectrum. Okay, but my focus there has been always on resource allocation and essentially thinking about what you do with the wireless resource in facing the physical characteristics of the wireless resource, and on the other hand, also facing the application as it comes from the top. And interestingly, that was a point in time when in cellular networks, we were just switching from pure telephone networks, which was the second generation, towards serving also data services. And that was 3G. Some people say the uneven cell network generations are always the ones that kind of like want to do something, but they don't really deliver on their promise. So 3G was essentially then also not a very good data network. We fixed that in 4G. And what I worked on for my PhD was resource allocation for 4G cellular networks. At 2002, when I began, we didn't know that it will be LTE, but we knew this is going to be the next generation. Okay, when I became assistant professor in 2008, I turned also towards critical machine-to-machine communications. So that's the basic question: how do we build wireless networks for industrial automation applications? That's what we started roughly 10 years ago. I'm also working in theoretical network performance models, in particular in queuing approaches, always driven towards design questions of cellular networks. Okay, and now most recently, like over the last 2 or 3 years, I've been picking up this topic of edge computing. Now, what really keeps me up at night, so this is all describing a little bit what I do, but when it really comes to what drives me here on a daily basis, it's the question, if you think about a communication network in 10 years, What are going to be the dominant applications in 10 or 15 years? What are going to run in the millions, in the billions over these networks? That's really what touches me, and that's really what I'm interested in. Okay, and I want to show you now today and also tomorrow a little bit some of the questions that are coming up here and how I think about that. I want to know also how you guys think about that. Please interpret these 2 days, so today and tomorrow morning, as a highly interactive session. So whenever you have a question, you just shoot. That's totally fine. Okay, good. So this is a laser pointer. Very good. This is a high latency presentation system, as it seems. Okay, so this is a little bit the outline of the lecture of today and tomorrow. So we're first going to do this high layer perspective. We're going to look at networks, cyber physical systems, and edge computing. I'll try to surprise you here a little bit. Let's see how that works. And then we're going to get more into some details, technical details on edge computing and wireless. And I guess this is where we're going to break today, if we're good. Perhaps somewhere in between here. And then tomorrow we come more to a concrete engineering research example. So how can all these challenges manifest in something? No, I say something very evil that we can publish. Perhaps also that we can build. We can talk about that tomorrow. And then we come to some conclusions and outlook. Okay, good. So we start with introduction to networks, CPS, and edge computing. So first question for you guys, and again, I'm also highly interactive, so I shoot also a lot of questions at you. So be prepared to answer. I want to know from you guys, what is that? I'm showing this for the second time now in a presentation. The first presentation that I gave 6 weeks ago took 10 seconds for someone to identify it, although I really invested time to cover it up. Spine. Yeah, so I already tried to improve covering it up, but I'm still not very good at that. Okay, that's the human central nerve system, the spine with the brain. Okay. Now I want to know from you, why do humans actually have that? You want to say something? I see that.
To send data from our sensorial organs.
Wow. Okay. Yeah. I never felt that way. Sorry for saying that. But okay, I'm saying sending data from where? From
our sensorial organs.
Okay, good. And why am I doing that? Did God just decide, oh, humans need data communication capacity, so let's put in the central nervous system?
It's a feedback control system.
And why is that? So, in which sense and why?
You make decisions based on what you see, and then you modify those decisions.
Okay, all right. And why? Why do I do that? Louder, sorry.
You don't have wireless communication.
Okay, good. But that doesn't explain why it's there in the first place. That just explains why it's wired, maybe. What's that thing doing for you?
Carries your weights.
Sorry?
It carries your weights, like the weights of the muscles and everything.
Yeah, that's a little bit part of that feedback loop, right? So muscles are in there. Is that, who said something? What?
To do tasks.
And why do I do tasks? To what?
To survive.
To survive. Ladies and gentlemen. This is all about survival. Why? Right? 20,000 years ago in the savannah, right? This is a common situation. Not so much in downtown Stockholm these days anymore. Maybe kind of like in a more in a synonymous way, right? So there are still predators out there, but they look differently than 20,000 years ago.
There are some lions near the royal palace, actually.
Yes, but they're not just, right? They're just not walking around like that, right? So I see a threat, right? And I process that with my central nervous system. And then that processing leads to a reaction. And that reaction is your fight or flight instinct, your fight or flight reflex in that sense. And that's essentially there. It's ensuring your survival. Okay, good. So let's keep that a little bit in mind. Let's have a closer look at here this central nervous system. So if you look at what that is doing, it's actually chopped up into a hardware part and into a software part. Now, your hardware are your senses, right? They're all distributed all over your body, right? You have communication lines, you have some processing capabilities, you have actuators, so the muscles, these are essentially actuators, not everything. Not all actuators in the body are muscles, but that's what's roughly there, right, in terms of hardware. And there's also some software, right? So we have in our brains representations of reality. So if I say lion, all of you instantly come up with a representation. No one knows if that's the same representation, but for all of us, in one way or the other, it's more or less doing the same thing. In particular, 20,000 years ago, when it was about survival. Okay, and on top of these representations, we run algorithms. Okay, so taking that into account, I want to know from you now the following. Are actually humans a CPS? You cannot say something. You're the organizer. So it's a simple question, right? It's yes or no.
I'd say no, because with a CPS, you'll need to separate the software from the hardware. I don't think any of us want to try that.
And what? Sorry.
I don't think any of us want to try that with our bodies.
Sorry, I haven't
I
understood.
don't think we want to try separating human software from
Yeah.
our bodies.
Yeah. Okay. And actually, I'm not deep enough into physiology to say if the software is actually really separable in a human from the hardware. But I would suspect that is the case, right? Because otherwise we couldn't change our opinions, for example. That's a different story. Okay, so you say no. And the argument is we cannot separate hardware from the software, and that defines a CPS?
Yeah, to me.
Okay, fine. Any other opinions? Yeah?
Why not separate us? In my eyes, it's life is software and our bodies are hardware.
Yeah.
It can be separated.
Okay, but that's a question, can it be separated or not? We don't want to get into that, right? We want to stay on track. Are humans a CPS? What do you think? Yes. Okay. All right. Who thinks humans are not a CPS? Okay. All right. Good. So there seems to be a majority more thinking we're CPS. It all depends on definitions, right? So let's pull out the definition. Right? And all you guys have seen that before. I've been discussing that over the last year with Martin. Down, up and down, not in the context of humans, though. So CPS is an integration of computation with physical processes, right, whose behavior is defined by both cyber and physical parts of the system. Embedded computers and networks monitor and control the physical processes, so the environment, usually with feedback loops where physical processes affect computations and vice versa. Right, so there's feedback, there's processing, there's reality. I'm interacting with reality, and there's a separation between the cyber domain and what really happens in reality. You're always operating only on representations of reality. Okay, so we can say humans, under this definition, it's safe to say humans would be a CPS. Albeit, from an engineering point of view, this is a super large and complex CPS. So your body is composed of 30 trillion cells, roughly. There are 200 different types. Each cell consists roughly of 1 trillion molecules. So, and this is all controlled by your spine and by your central nervous system. So it's a very, very sophisticated CPS in that sense. And that explains why humans do what they do these days. Okay, now I want to know the following from you. So what ensures the survival of the human CPS? What ensures that? All right? So under this perspective that it is a CPS, what makes us going? Why are we still here? Genetics. So there's an evolutionary perspective, right? Okay, I agree. Adaptability. Who said that actually? Yes, adaptability. We learn, right? So now it gets dangerous because we're drifting towards this black hole these days in academics, which just by gravity pulls in everything, and it's called machine learning, right? Let's try not to get too close to that, beyond the event horizon, then we don't get out of that anymore. But true, adaptability. Okay, but there's more. Think about the example with the line. What is important in this CPS? We need to have energy supply. Agreed. There's a line over there, right? There in the back corner, right? No, not you, and let's just imagine it. What ensures my survival?
Perception.
Yeah, and more. I have that feedback loop, ladies and gentlemen. We just talked about it, right?
Flee.
Say it, yeah?
Flee.
I need to flee, and I need to do that in time, fast. Fast is relative, right? But I need to do that in time. There's a real-time component here. Huh? And that's a statistical thing. So your system, your body evolved in a certain way that you're optimized towards what humans typically encounter. Huh? Change the gravity constant on this Earth. Huh? Let's move to a different planet. And all of a sudden, all our reflexes are going to be wrong. Huh? Because things are either happening faster or slower. Slower would be actually good. Huh? But faster, who knows? Huh? Okay, so there are dynamics. We try to react to these dynamics, and we need a real-time response. Otherwise, we don't survive. And it's a statistical game. Huh? So that's what's happening, right? What's also important is we need a sufficient representation of reality. Huh? It's not important what color the line has. It's important that there's a line. Huh? Okay, we need adaptable control algorithms, but then what I said, the most important thing is we need this feedback loop, and that must be capable of providing a real-time response. That's the most important thing. That ensures survivability and your interaction with reality. Okay, good. Now let's stop with that, and let's go into the domain of ICT, silicon-based ICT systems. So I don't want to talk with you about an individual embedded system that is deployed somewhere and is doing something specific there. I want you to think big. And big means networking on a global scale. Now, if you look at telecommunication systems, and these are now just, in a sense, the communication lines that have been put in. If you look at the evolution of telecommunication systems, and we're now talking about roughly 200 years, when the first engineered telecommunication systems were coming up. They were not electronic, they were mechanical. They're so-called optical semaphore lines. It's a little bit like the Indians doing their stuff with the smoke. It's just not smoke, but it's big mechanical constructions. Who's from Stockholm? Is anyone actually from Stockholm except from who is from Stockholm? So we had, for a time, in front of the Technical Museum down in Martin, this big field where the horses always run for the National Day. Huh? Djurgården, exactly. There was in Djurgården, like 200 meters away from the Technical Museum, there was one of these optical semaphore lines still there. I don't know if it looked a little bit like a guillotine, just much bigger. Does anyone remember? No? Okay, it doesn't matter. I'm always jogging around there, so therefore. Okay, so roughly 200 years ago, we introduced communication systems. Right? We have a history of 200 years of telecommunication systems. Telecommunication systems evolved in waves, and these waves are always defined by applications running on these systems. The purpose drives the telecommunication system. It's never the other way around. The purpose of the first wave of telecommunication systems was essentially telephony, or in the more general case, human-to-human communications. People wanted to exchange messages with each other in one way or the other. Okay. Did that have like 150 years ago or 200 years ago, when we talk about these optical semaphore lines, did that have an aspect of survivability in there? Yes, maybe. What?
It's better than the telegrams.
Okay. 200 years ago, there was no differentiation between telephony and telegrams. It's just messages sent from humans to humans. And the alternative to sending it over an engineered system is to send it by horse.
But this saves the time.
And it saves time, and that's why it came up. Yes, exactly. It was faster than the horse. Yeah. But what is it doing for me? Why am I, where's the survival aspect here?
Save the life also.
Yeah.
If it's accident.
Say maybe what?
If it's some accident.
Okay, yeah, like Chernobyl, right? But 200 years ago, that's not there yet. So what has dynamics that generate a threat to survivability 200 years ago that necessitate a communication network? Wars. Okay. Who are always the first adopters of new telecommunication equipment? There are two groups. Military. And someone said business. Who said business? Which part of business? Finance. So the stockbrokers, the guys speculating on the development of prices. And interestingly, these two groups have typically almost unlimited financial resources. And that's always why they're the first ones that can tap into any new telecommunication infrastructure, that can build it, because they don't care about costs. 200 years ago, the first optical semaphore line was connecting France and was exactly there for that purpose, to convey strategic military information on the one hand for the state, and on the other hand for those that could afford it. These were, you need to say, like every 5 kilometers you had like a tower which was like 30 or 40 meters high with kind of like a metal construction on top. It's a little bit like an ancient SMS. It's really interesting how they worked. This was a huge investment, and so relaying a message was very expensive. And the only other ones that could afford that were investment brokers, stockbrokers, that were interested in the price of bonds. They were using that at that time. And then this evolved later on into more and more sophisticated applications, right? And then at some point, we got this telephony functionality, and that's like roughly 120 years ago. And here in Stockholm, this was one of the places among some places in the US where it really came up first on a larger scale. And then this became more and more sophisticated. Key here is, it's always humans directly in touch with humans. That was driving telecommunication networks for the first 170 years, roughly. Okay, now we have the second wave of telecommunication systems, and that's the internet. What is the business driver here? It's not really said so much here. Why did the internet take off so much? What was, where was it, where is it giving us an advantage? Say again? Information. Yeah, but that information also applies here, right? So, hold on, 1 second. Let's first ask the following question. Where is a bigger investment relatively to world GDP? Was that in the first 170 years here, or in the later 30 years here, up till today? Later. So this is much more expensive to build than the first one. That means there must be a bigger business driver here. Who said news? Yeah, like Trump, the next Twitter message from Trump, right? Yes, news. Huh? What do you mean by markets?
The knowledge about prices.
Yes.
At other places.
Okay. How is that done? How are markets organized in 1970? 1-to-1, right? For example, this New York Stock Exchange. How does that work?
One place.
Yeah. So there are people. Some people want to buy. Some people want to sell. What's in the middle? Who's doing the arbitrage? Who's determining the prices? Who's doing that? Brokers. Huh? They kind of like level between sell requests and buy requests, right? How's that done today? And why? What do we do? What do we do? Huh?
It's distributed. So
Yeah, okay, sure, it's distributed. But what's the key thing? What happened to these guys in the middle doing the arbitrage? Who said what? Who said no business? Yes, there's a level of automation happening. They're gone. It's a server. And this not only applies to stocks, this applies to books, travel, everything you buy on Amazon, blah, 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 blah. All these middlemen, all these middlemen companies are cut out here. With client-server applications, you have all of a sudden the possibility to store, manipulate, and retrieve information at a central place and provide that worldwide. And this has a huge business impact, and that drives this second wave of telecommunication systems. But on the client side, it's always still the human sitting there. It's still the human who's kind of like in front of the stockbroker application, right? And running this application. It's just not communicating with another human. It's a server by now, right? Okay, and all you're doing today with your apps, WhatsApp, WeChat, whatever it is, this is all still this good old client-server stuff. Just coming a little bit in a different form. Okay, so now the key question is, this is where we're standing today. Key question is, what comes next? What comes next is that we're going to digitalize also this client side, in a sense. We already have the server on the one hand, now we're going to digitalize also the client. That's what some people think, and that manifests in the digitalization of the rest of reality. Wherever it makes sense, wherever it gives us kind of like a competitive advantage or an advantage of survival. Today, of course, with billions of humans, it's not so much about survival anymore, fighting against the lion. It's more about getting a relative competitive advantage to some competing peers. And that can be, meanwhile, in the global world, competing peers all around the world. Okay, so let's have a look at what that means. So this is how a contemporary network looks today. This is pretty much how it works everywhere around the world. So you have your handhelds, and all of you have handhelds. They're connected via wireless networks, LTE, 4G, 3G equipment, right, to an access point, to a base station. Right? This goes through the backbone of your internet, of your mobile network provider. Right? These messages are routed somewhere, and then they hit kind of like the global internet backbone in one way or the other. And sooner or later, all these data requests kind of like end up with the cloud center. 90% of the traffic is flowing in that direction or backwards. Only 10% of the traffic is kind of like going between purely the handhelds, the pure telephone calls. That's almost no traffic in comparison to all the data stuff that you're doing today, and that always goes up to the cloud and comes back from the cloud. This is all oriented towards first and second wave telecommunication systems. Okay, and what we have from a functional perspective, you can say you have processing capabilities over here. Then all the stuff in the middle is just doing some transport, and you have processing capabilities again here on the other side. And you're between these two processing points, that's kind of like the end-to-end principle in the internet. Between these two processing points, data is like all the time flowing back and forth. That's kind of like the game that you see in large-scale telecommunication networks today. Is that a question, or is that more?
No. What kind of processing is applied to at the other end in the call center?
You send your WhatsApp message to your friends. That first goes here. Mr. Zuckerberg wants to see that and have that, and this is where he's collecting it. And only then it goes to your friends. And everything else is exactly the same thing, and it's for exactly the same reason. All these companies, the big Silicon Valley, kind of like Western US-based companies, but not only them, right? They all want to collect the data, and this is where they collect it. That's where they grab it. And they put up like tunnels through HTTPS, such that only though they get it. No one in the middle can see it. That's how the world is today. Okay, good. So this is how the network architecture looks today. Now, let's get a little bit more into the details on edge computing and wireless and see how that is connected to this notion of a higher degree of representing the reality. So if you look at this contemporary network, there are a couple of challenges if we now want to put in these closed loop applications, these CPS applications, what's essentially running inside of you all the time. So the first thing is the real-time response of your infrastructure. That's way too high as it is today. But we need relatively low latencies and also high reliabilities over the loop. There's no gain for you if you see the line and your eyes are somehow catching that information, but only sometimes they're forwarding that information to your, to somewhere to your deeper brain parts. That's a highly reliable and low latency communication link. There's also no help if that sensory information is forwarded within, let's say, 5 to 10 minutes to your brain. The dynamics outside in the world are just higher. You need to react faster. That's why you are the way you are. But in this, in the setup here, and this is actually really high latency, in the setup here, these latencies between cloud and whatever is going on here on the left-hand side, that's way too high today. And the next thing is that this transport here is run by the so-called Internet Protocol, by IP. And IP is exactly the opposite of what we need. It's not giving you any latency guarantees. It's not giving you any reliability guarantees. It's only there to provide a kind of like in a distributed manner, worldwide connectivity. IP has been built with the idea in the mind that if someone drops a nuclear bomb on the US and a couple of cities are taken out, the network still survives. That's the core idea, engineering idea that essentially is behind IP. Okay, so that's not the backbone to go. Okay, we need also corresponding compute and communication elements. Right? So we have this low latencies over the loop, right? But the loop decomposes into individual elements, communications and computations. So whatever requirements we have on the loop, they translate into the individual elements. Okay, good. And as said, cloud computing, 4G networks, and IP, this combination is just not giving you what you need. That's not sufficient for many CPS applications, also other applications. So what's the answer? Where are we going? Where we're going is, if the prophet doesn't come to the mountain needs to come to prophet, right? So instead of putting all our control CPS applications somewhere into the cloud, we're bringing these compute resources close to the endpoints. This is a little bit like saying, oh well, right? So, in certain situations, it takes too long to forward your sensory information to the brain, and therefore you have kind of like local compute already along the route to kind of like do something up front. And in fact, that exists. So you have reflexes sometimes, and some of these reflexes are not generated in your brain. They're actually generated in your spine or also at other places. So that's local compute. But this local compute, this will be there kind of like on a ubiquitous manner. So in 10, 15 years, it will be totally normal that when you're moving through an arbitrary space, and let's say in civilization, and what I mean by in civilization means there's a mobile network provider there, and the mobile network provider deployed the infrastructure. So as you're moving through this space, there will be a huge kind of like data cloud always moving with you, hopping kind of like from edge node to edge node, and you will constantly have applications running, but they're not running on your cell phone anymore. They're running here on the edge node. So you will have in your data plans the possibility to kind of like run applications, execute applications, computational applications, somewhere in the infrastructure. That's where we're heading, and that will mean that in 10 years, this stuff is gone. There will be no cell phones anymore, as you know it today. These bricks that we're keeping with us, that we're taking with us, they're all gone. All the compute will be mainly happening here, mainly. Not over there anymore. Over there, we only collect, but no computation in the cloud centers anymore. Okay, so if the edge nodes are now closer to the endpoints of your applications, that has some benefits, and these are the benefits. This is an experimental measurement set that was published by a colleague of mine at CMU, Carnegie Mellon University, where they looked into a different type of closed loop application. I haven't been really explaining that. So when we think about CPS, we think a lot about control, right? Closed loop control applications or combinations of different control applications, right? Systems of systems. But there's a different type of closed loop application which has exactly the same characteristics, but it's in a completely different context, and that is where you put humans into the loop. It's your augmented reality. That is exactly the same thing. You have sensory input, typically a video stream, that is analyzed somewhere, converted into representation of reality, And based on that representation of reality, we then give some perceptual feedback. All right? So, for example, a trivial example or a harmless example is, I want to cook something, a new Chinese dish tonight. All right? I know cooking, but I don't really know the Chinese dish and the recipe. I can have like an AR glass in front of me that is recognizing what's going on and exactly guiding me through the way how I put together this dish and how I cook it. So this is something I can do, and there I'm capturing reality and I'm guiding the human to do a task. Right? I can put that also into a completely different business-related or also military-related context. It's totally clear. Right? So with task guidance, as we call that, right? I could, for example, also reduce the time that I need to get new workers into kind of like dealing with a new manufacturing site. I can reduce the time from perhaps months to days, maybe even to hours, if task guidance is there. Right? I can do the same with soldiers on the field. Okay, so human in the loop and kind of like plants. Control plant, to be controlled plants in the loop. These are the major applications that are coming up that will dominate here the applications here on the edge. And where it's always about, at the end of the day, collecting the state of reality and representing the state of the reality here at the edge nodes. It will be very interesting to see how do we represent reality, what do we do with that information in addition. And if you're asking yourself what's the major kind of like driver, technical driver for this architecture, then it's always this actuation feedback in time, the real-time feedback capability that is coming up. That is the most, let's say, powerful thing that is now coming up and enabled by these edge nodes. Okay, so looking into this data, so here the colleagues from CMU, they have been looking at different human-in-the-loop applications. Don't be too much concerned about these names. They have different they're playing around with different task guidance tools. They're all in this augmented reality, human-in-the-loop style. And they go here kind of like from pool up to sandwich. This is the cooking example that I was making. And they have been looking into the responsiveness of the infrastructure, depending on the infrastructure running the corresponding detection and perception generation algorithms, either on the cloud or on the edge. Cloudlet is just a synonym for the edge. I think you're all getting the present. I mean, just continue to take photos, but I think we're distributing the slides, right?
Just mail me and I'll...
Yeah, okay, so I'm happy to provide the slides, no worries. Okay, good. And what you see is bringing the edge resources close to the application endpoint cuts out a lot of these blue and green communication latencies, where your response times towards the cloud are typically in the hundreds of milliseconds. You can all of a sudden crunch that down to 70 milliseconds, so something below 100 milliseconds. What you're always cutting out is, of course, the network delay. You're not getting rid of the delay incurred by the computations. Of course, the computations, for example, to detect that you're doing in a recipe now something wrong, that's always the same, if it's happening at the edge or if it's happening at the cloud. There's no difference. But your communication delays, they're vanishing. And in different cases, depending on the application and the rate requirements of the application, this can be significant. These can be really, really big chunks that you're cutting out here. That's what you're seeing. Okay, good. So that's where we're heading. And I would say in telecommunications, maybe even in the, for sure in the telecommunications industry, this is by far the most exciting business struggle that you're seeing right now. Who's going to own and commercialize edge computing applications, right? And there are these Silicon Valley companies, right, that all know very, very well how to commercialize software-based systems. Google, Amazon, right? All the cloud providers, the big cloud providers are there, right? They know how to do it, but they don't have the sites, right? If you want to do edge computing, you need to be close to where the action is. Those that have the sites are the mobile network providers. Vodafone, Telia, Tele2 here in Sweden, right? O2, and so on and so forth. Unfortunately, these guys are terrible in commercializing software-based systems. And that's exactly why they're in the miserable situation they are, because they only provide bit pipes over the last 15 years. They never came up with any real innovation. Okay, and they're now fighting because they had one have the sites, but they don't know how to do it. The other ones know how to do it, but they don't have the sites. And this is super interesting how this is going to play out over the next 2-3 years commercially. Okay, good. So I've been already talking. Where are we time-wise? Okay, good. I've been already talking a little bit about cloud versus edge computing, right? So the main thing is, right, in cloud computing, in tendency, your latency towards you reach a point of computation is high. In edge computing or fog computing is very low, right? And all that then goes on and so on. Basically, it's all relatively straightforward. When you talk about typical application domains, if you cluster them according to the volume of data transmissions to the server, that goes here from small to large, and with respect to the real-time requirements, from small to large, meaning large, we need small delays, so the requirements are really large. So where edge computing is going to be very beneficial is kind of like in this domain, right? Where you have large volumes and you have very small delays that you need. And this is typically augmented reality. Virtual reality, to some extent, perhaps also CPS, but CPS, the basic control loop, right? You all know that. The basic sensor reading, a basic activation command is typically not that big. Right? There's a completely different story if you run object detection on a video stream. Okay, good. And therefore, like machine control, augmented reality, this is kind of like what we're anticipating where these closed loop applications, where this closed loop principle is going to come up. Okay, good. So that's where we're heading in terms of mobile networks. That's the next big thing in the sense of empowering mobile networks to introduce vastly different application types. Now we overlook one thing in the challenges so far. We just talked about where's the compute going to happen, and the compute is going to come from the cloud nodes, right? How do I do that? I want to go back here. Wonderful. So the compute is going to come back from the cloud centers closer to the endpoints. But there's still one thing in the way, right? Because not only beneficial if we in principle could have a real-time reaction, right? If there's a threat, let's say 10 years down the road, your kid is going to school, right, and has this kind of like this assistant application with it, which warns it if there's a car showing up, right? So that's the modern lion in 10, 15 years, right? It's not the lion anymore in the savannah. It's kind of like the autonomous car coming around the corner, no one sees it yet, right? But we're on a critical trajectory and we're going to hit, right? So how do I detect that, right? And how do I make sure that then the activation command to the kid or to the car comes in time, right? One answer is bring the compute closer to the endpoints. That's for sure going to do the job. We already know that. The other issue is when I do this computation, right, I want this, this feedback here actually to reach the corresponding actuator, your kid in 10 years, the autonomous car in 10 years. I want that message to really be transmitted reliably. That must be received in time. Otherwise, we're having a problem. Okay, and that's of course all going to be wireless, right? Just because wires are such a hassle. No one wants wires. Okay, and is that actually a challenge to make that wireless? Who said yes? Who said yes? Yes. Do you know why, actually?
Because
now we're back to why.
Propagation, medium, interference, and a lot of other...
Yes, exactly. So the wireless communication channel here is a highly stochastic thing. So for the last 30, 40, 50 years, we're trying to battle it. And we're still not at the point where it's deterministic, and it will never be deterministic. But we're getting better in moving its stochastic behavior, let's say, in a favorable manner. Okay, so what happens on the wireless communication channel? Why is that so? We said the propagation medium, you said interference, something like that, right? So, okay. So what's the basic problem with wireless? I mean, come on, right? It's like Marconi. Does anyone know who Marconi was? Marconi was a company in the UK, but that's not what I mean. There's a guy called Marconi.
Guglielmo Marconi.
Say again, what?
Guglielmo Marconi, I think. I don't know the Italian pronunciation, but he's the wireless guy.
He's the wireless guy. And what was his problem? Where was wireless communications coming up?
He was the first person to transmit something from over the Atlantic.
Yeah, that's a bit far, but the ocean is the right thing. Wireless communications, as always, right, came up in the military context. And the problem that the Britons had was to communicate commands to ships. And that's where wireless communications came up. And Marconi, roughly 100, 120 years ago, I think so, I forgot the exact year, but roughly around that time, he was the first to say, okay, we could do electromagnetic communications. We could communicate signals electromagnetically through wireless waves. Okay, good. So, right, so we're for 100, 120 years dealing with these wireless communication channels, and it's still not deterministic. Right? So where's the problem? What's the issue here? Yes, exactly.
The energy dissipation in the space
Exactly.
and not
Yeah.
along a line.
Yeah, exactly. Yeah, it's not guided. When I transmit from an antenna an electromagnetic wave, this wave goes everywhere. That wouldn't be a problem if it would just go all the time exactly in that direction, because then only exactly one signal would receive my receiving antenna. Sorry for pointing at you over there in the corner. But that's not how God made the world. God decided all the stuff needs to be reflected, or at least certain parts of these electromagnetic radiation is reflected, and these reflections all recombine in the antenna over there. In acoustics, we have exactly the same thing going on. And sometimes you can hear that. How's that called? An echo, right? So sometimes I have the situation that I speak, or more generally, I'm shouting, and what I'm shouting is kind of like reflected, but it's reflected with a significant delay. And this reflection of the delay and the fact that any propagation scenario, any propagation environment has kind of like a random delay. When these reflections come into your antenna, that leads to total chaos in the wireless communication channel. Essentially, you have these recombinations. And so these are all electromagnetic waves. So essentially, these are sine functions. You can think of them as simple oscillators. It's much more complicated, but this is a very instructive way how to think about it. And then sometimes when these waves all recombine at a single antenna, they recombine so-called coherently, so in time they fit together. And then actually they add up, and you get an energy gain out of that. But oftentimes you have the situation where they're recombining out of phase, and then they have the capability to completely eliminate themselves. And this is something all of you perhaps have been witnessing. So perhaps you know that situation where you're standing in front of a traffic light with your car, you have the radio on, and all of a sudden your radio signal is gone. And if that happens the next time, please do the following. Put in your first gear, just roll 10 centimeters. And then typically your radio signal all of a sudden comes back. And if that happens, then you know you were exactly a victim of these signal copies of the electromagnetic signal copies, recombining in a destructive manner at your antenna, where your antenna is positioned. Okay, so that leads, in practice, to what we call fading. This is an illustration of a fading signal over time. And you see here the magnitude of the power received in decibel, but that doesn't really matter. What matters is that you have here these swings of your received energy, and this is just 1 second. And within 1 second, you have swings over, let's say, 30, 40 dB. So that's a factor of 1,000 or 10,000. And this is just happening kind of like randomly. And it's happening frequently. It's happening very, very often within time. And so, if you're in this augmented reality application, your kid now needs a signal, don't move forward, stay where you are, because otherwise you're going to be run over, or you want to tell that to the autonomously driving car. But your wireless channel is right now in this situation here, or here, or here, you have a problem sticking the message through. So the key question, a very significant question that over the last 5 to 10 years a lot of people have been working on, is how to make this wireless communication channel more reliable. And with that, I actually want to stop, because that's what we're going to talk about tomorrow. And then we're also going to talk about tomorrow more an integration of wireless communications and edge computing for control applications. Any questions so far? Then thanks for your attention.
Questions seem to cancel each other.
No, I don't think so. I don't think so.
Okay, thanks a lot.
Yeah, sure.